Hi everyone! Today I want to take you on a time traveling journey and we're going to use this rock as our time traveling device. This is called Pudding Stone and it's a super cool rock with all kinds of different colors in it. And it's called Pudding Stone because it reminded the British when they first saw it of steamed pudding. So if you imagine like berries and raisins and suet steamed together in like a cake-like texture, that's what it reminded them of. But its technical name is a Jasper quartzite conglomerate, which is also a mouthful, but it's actually simpler than it sounds. A conglomerate is a rock that's made up of all kinds of other rocks that get cemented together. The thing that is cementing them all together, or the matrix all those little berries are sitting in, is called quartzite in this particular case. And then the little berries themselves, so those little red ones, are made up of a material that's called Jasper. So it's a Jasper quartzite conglomerate. There's also other little things in there. You can see there's these black chunks of chert. In this case, when chert is this black, we would call it flint. There's also white quartzite pebbles. They're kind of harder to see. There's also yellow semi-transparent quartzite pebbles. And sometimes there's hematite in there too, but you can't see that really right now. So there's the red jasper, the black chert and or flint, white quartzite, and yellow semi-transparent quartzite in a quartzite matrix. And here's one with just one little berry, but you can see that kind of fatty, suety, cakey look. It's kind of got like a bit of transparency. Sometimes it's kind of this pinkish color because I think it gets a bit of iron on it when it's in the lake. Sometimes it's more of a stark white. This is a pudding stone actually with no berries in it, but it is definitely the same quartzite from this formation. Here's one that's actually got like a purplish tone to it. And they just come in all kinds of colors, but the thing that's exciting about them is all these beautiful little pebbles inside. One of the things that's really exciting about pudding stones is they're old. They're 2.2 to 2.4 billion years old. It's incredible. Our bedrock locally, the sedimentary bedrock, is 420 million years old, so it's just young compared to this. The Earth itself is 4.5 billion years old, so this is like half as old as Earth itself, which is so cool to see. Rocks get recycled a lot in the Earth's crust and kind of remade into other things, either through geological processes or biological processes. So to see old rock this old isn't super common on planet Earth, but we get really old rocks in the northern Great Lakes, northern Ontario, northern Canada region. So it's kind of cool to see because they have pieces of history, which you'll see in a minute, that are really, really neat to be able to look at. So how did this rock form? Well, it probably formed, geologists suspect, in kind of an ancient river opening. So rivers and streams are major agents of erosion. They erode the stream bed themselves, and anything that's weathered and comes in kind of gets brought out towards lakes, rivers, and eventually the ocean. And so that's sort of how they weather the continents. So if you imagine all that stuff that a river is weathering, at the mouth of that river that stuff kind of all collects, sometimes in a big kind of outwash or sometimes in like a system of little braided rivers that have broken up. But all of that stuff that's come out would have consisted of these, all these pebbles I just showed you, and then a bunch of sand. And it's really a beautiful thing to imagine that river with like bright red pebbles and black pebbles and yellow pebbles sitting in sand. What a sight that would have been. But eventually that kind of mix of pebbles and sand got compressed into sandstone, which is a sedimentary rock. And the reason that can happen is because sand is made up of quartz crystals, and so you can kind of compress it and they get kind of tight together. But it can be compressed even further. So when you heat sandstone and put it under pressure, it can become a metamorphic rock called quartzite. So because sand is made up of quartz, when you heat it and put it under pressure, those quartz crystals can kind of reform. And the Earth's crust, there's always heat coming out of the Earth's core, And then there's all kinds of processes from like other rocks forming on top to mountain building to tectonic plate movement to volcanic processes. Lots going on that creates pressure and heat. And so you can turn this loose sand and pebbles into sandstone over time, and then that sandstone can get heated, pressurized, and turned into quartzite. So it's an incredible thing to think about, that journey of being at this ancient riverbed, and now we're into a phase where we've got this huge patch of rock in, which is actually from northern Ontario. So pudding stone outcrops in sort of the Sault Ste. Marie, Bruce Mines area, St. Joseph Island, that kind of thing. But because we've had several periods of glaciation in North America, those glaciers have like since exposed, like they probably got covered up long ago with stuff, but they've exposed the pudding stone. And they've also kind of, it's gotten broken up and dragged other places in little pieces like this. So it's gotten dragged in, you know, as far south as places like Kentucky. You get a lot of it on in Michigan, but we do get some of it as well on the Lake Huron side. Now the glacier sort of predominantly moved in this direction, but there was also, when that glacier melted, lots of lake water movement, and we've had 10,000 years of waves and currents, so the rocks get moved around a little bit more. So along the Lake Huron shore you can often find this pudding stone, even though it actually comes from kind of this Sault Ste. Marie area, which is really amazing to think about, that it's taken that journey from being sand and pebbles in an ancient, over 2 billion year old river, to being sandstone, to being quartzite, to being covered by stuff, to being uncovered by glaciers, to being dragged by glaciers to certain areas, to eventually roll up on a beach for me to pick them up and be talking about it today. What a journey that is. But what's neat is there's some stuff inside the rock that's even older than the rock itself, because of course those pebbles in the bottom of that riverbed had to come from somewhere. So one of the ones I really want to talk about is the Jasper. So this red Jasper, it's hard to sort of see, but it's got, you can see it's dark to light, and it's got this really fine lines and gradation. You can see a bit more obvious layering in this one. So this layering probably happened during the Archean period, Archean eon, sorry, not period. And this was a period, eon of Earth's history that was kind of interesting in terms of life, and when we think about the evolution of life. So there was a period of time where there wasn't a lot of oxygen in the atmosphere. It's kind of hard to imagine. We always think of our planet as having this 16 to 20% breathable oxygen atmosphere, M-class planet, if you will. But it didn't always have that. When the Earth first formed, after sort of all that stuff condensed after the Big Bang, it was what they call a Hadean Earth, or a Hell Earth, because it was all fire and brimstone. And that eventually kind of settled down, and life first started evolving probably around 3.7 billion years ago. And that life was predominantly cyanobacteria, which produce energy through photosynthesis, just like plants do. And so they started kind of outputting oxygen, just like plants do. But at first, there was so much iron coming out of hydrothermal vents from the Earth's crust, and from the Earth's core, rather, and iron coming off the continents, sort of weathering off the continents into the ocean, that there was lots of this kind of iron floating about. And iron, it really gets readily oxidized by oxygen. So all the oxygen that those cyanobacteria floating around in the ocean produced would probably bind to that iron, or they would actually bind it to the iron themselves, and that would eventually, that sort of oxidized iron would just sort of fall to the bottom of the ocean floor. And you can see that in this really layered one, all these different layers of stuff that's just fallen down. And there was probably some sort of gelatinous goop at the bottom of the ocean that consisted of silicon and that kind of stuff, and it eventually became silicon dioxide with this sort of iron oxide in it. Because Jasper, it turns out, Jasper, as well as the chert or the flint, as well as these quartzite pebbles, as well as the quartzite matrix, all of this that I'm talking about is quartz, silicon dioxide. Jasper, chert, quartzite, quartz, all the same thing. Just a little bit different in terms of some of the extras that are in there. So we're back into this ancient environment 2.7 billion years ago. We've got all of these life forms producing oxygen. It's reacting with iron. That's falling to the bottom of the ocean and creating this, this sort of banded iron formation. And that eventually gets broken up into pebbles, ends up in this river, and the process goes through, as I said before. So it's just incredible to me. Not only is this rock stunning to look at, it's beautiful, it's got all the colors of the medicine wheel, and super bright red, and yellow, and black, and white, cemented in this nice matrix, but it's also got this incredible history that tells a whole story about the history of Earth, and really humbles us in the perception of time. So it's kind of amazing.